All right, today we're going to be starting a brand new unit on gases. States of matter being solid, liquids, and gases. Gases gets its very own chapter because of the unique way in which they behave. So let's go ahead and get started with a little presentation on this. And the first thing you're going to want to get some really good notes on these. So get all the parts of these, and again, pause if need be. But the huge difference between gases versus liquids and solids is that they'll fill whatever container that they're in. And you can scrunch them down. They're compressible, and they have very, very low densities compared to their liquid and solid counterparts. And remember, these could be the same substance existing in these different forms of matter. Today, we're going to focus on one of the measurements of gas known as pressure. Now, on a physics level, we define pressure as force per unit area. So make sure you get that little equation down. I think a little sketch of this diagram is kind of interesting to include as well. If you think about this, as you're sitting in your desk, and it's off a little bit, should be right over there a little bit more, but as you're sitting in your desk, there is a column of air sitting down on top of you. You could just say a meter by a meter, that's pushing down on you at all times with an exceptionally high mass, 10 to the fourth kilograms of weight pushing down on you. No wonder you're so tired at the end of the day. But you want to put that into the American units. It's 14 pounds for every square inch on your body pushing down on top of you. So in class we're going to do a couple demonstrations for those of you that can make it, to show just how strong that pressure is. And then we talk about that weight per unit area for atmospheric pressure. And we're going to talk today about several different ways of measuring pressure and units that we use. And obviously it's going to involve something like force per unit area at its core. So hopefully you remember from physical science, or some of you even in physics, F equals ma, that force equals the mass times the acceleration. That is known as Newton's second law. That if you really want to figure out the force acting on any entity, just take the mass in kilograms, the acceleration due to gravity. You were probably given 9.81 meters per second squared. That gives us a little more accuracy to it. And when you take mass times acceleration, kilograms times meters per second squared, that seems a little cumbersome. So in honor of Newton and his second law, we call that force unit a Newton, and a capital N is used for the abbreviation for that. Now, we'll further take that into what is called a Pascal. A Pascal, one of them, is 1 Newton per meter squared. So remember, it's force per unit of area that's being covered right there. So this sort of expands on that force and includes the area portion of it, and it's called a Pascal. A lot of times biologists will use something called a bar, which is about 1 atmosphere of pressure, and it's equal to 100 kilopascals. that you would, that kilo prefix, of course, means 1,000. And then 1,000, those 3 zeros plus those 2 gives you your 10 to the 5th pascals. So important units to understand. Now, one of the real easy ways to measure pressure is to take something. They'll use mercury usually for a couple of reasons. That number one, it doesn't freeze, and you could see what the atmospheric pressure is on a cold day, and it doesn't boil or evaporate very much. So it makes for a decent barometer. Now, the drawback of using it is it causes permanent nerve damage. So that's definitely something to shy away from. And we have many other digital ways of figuring out. You can pick your phone out right now and figure out what the atmospheric pressure is in Red Wing. So, but if you had a glass tube and you filled it with mercury and then inverted it into this pool of mercury, the mercury will come down because gravity is going to pull it down. That's what the red arrow is. But then the atmospheric pressure is going to push it back up. And we can measure how many millimeters of mercury that is. You know, on a standard day, and a low pressure comes in, that mercury will drop down a little bit. Now, there's no pressure up here above. This is a vacuum. Very difficult to create in nature, a vacuum. But if you measure the height of that mercury, that is one of the ways of doing a pressure unit. Now, in terms of defining pressure, we'll use this graphic. Here you have some gas molecules, all different size and speeds. Interestingly enough, the smaller ones are going a lot faster. The larger molecules are moving slower. But let's say this little thing right here was a plunger that would fall due to gravity if there was no pressure inside there, if the gas molecules were not moving. So if you were able to turn those into a liquid, this plunger would come right down. So it's actually the collisions that are causing the pressure. So this gas molecule hits that plunger and hits the container, and maybe if it was a flimsy container, it would collapse if it didn't have gas molecules inside of it. So these collisions with the side of the container ultimately are what cause pressure. All right. Now, here's a nice list of the pressure units that we're going to use and that you should be able to use interchangeably. Each one of these could be a conversion. So we'll go with 3 sig figs on most of them. So those zeros are significant. So 1.00 atmosphere. We'll use ATM, not the money machine, but the atmospheres of pressure. And this, as we just mentioned in the previous slide, you can measure this in millimeters of mercury. Now, I want to point out something about a significant figure. This is a little cheat you can use if you wish. You don't have to use it, but that 0 is significant. So you can use a bar to make that 0 significant. And so this would be 3 significant figures. Now the other way to do that, of course, is to go 7.60 times 10 to the second. And that would be scientific notation. And then you have a trailing 0, and you wouldn't need the bar. So 7.60 times 10 to the second millimeters of mercury. It's just a little more cumbersome. So a lot of times you can go 760. And notice millimeters of mercury can also be named torr, T-O-R-R. And then we had our kilopascals, which you know were related to a pascal, which is related to a Newton per meter squared. Turns out 101.3, same as I think KDWB on the FM, if any of you still listen to the radio in your car. 101.3 kPa. That's 1 atmosphere of pressure. That's how many kilopascals are pushing down on you on your average day. And as I mentioned, 14.7 psi, which is pounds per square inch, is another way of talking about a pressure unit. So know all of those, and then you could use those to convert. If you were given torrs and you wanted to convert into kilopascals, you have your conversions right there. 760 torr equals 101.3 kPa. So this can be a very useful tool for us in making these conversions. All right, now the next video we're going to introduce manometer problems. There is an attached worksheet that goes along with these. If you have a printer at home, I would recommend making a copy of the front and back of this worksheet. That way you have the questions and the answers in the same place. Or certainly you could use the online form of the worksheet and your notes on the test. But it'd be kind of nice just to have that worksheet available. So use this time in between these two videos. This is the first of two videos today to go ahead and run a copy of the front and back of that worksheet, and then you can put a lot of the notes that we're doing on what a manometer is can be right there on your manometer worksheet, which you will be turning in. Okay, so end of the first video on gases and pressure, and second video is going to kind of take you through how to do manometer problems.